Great. So when I was asked to do this talk, I had to come up with a title, and I still didn't know what I was going to talk about. And I had an old paper that Ron Lee and I did many months ago that I didn't want to present again. So I thought I'd do something new. And I think I said demography after the pandemic, which left the title very open. I could have talked about the future of the field or the future of demographic behavior. And then in my abstract, I think I said I would talk about mortality, fertility, and marriage. And then I found out I only had 30 minutes. So I'm going to stick to fertility and marriage, and I have a new title, Rebirth After Disaster, Models of Post-Pandemic Fertility and Marriage, with the emphasis on models. I don't know what will happen, and I think if this talk is a success, at the end of it, you will also not know what will happen. That's the goal, is to show different possibilities and how our models are very sensitive to small changes in assumptions, and how we could get a lot of things could happen after the pandemic. Let's see. I want to thank especially Paola for inviting me and for organizing this event, and of course to the Wittgenstein Center and all of its affiliates for setting up this conference. And then this talk, although my name is on the title page here, I've talked a lot with Ron already, and I've been doing a lot of mathematics with Tom Cassidy, and my new postdoc, Nathan Seltzer, has worked on this kind of thing involving Hurricane Katrina in New Orleans. And so they've all been super, super useful, and they deserve credit for what is valuable here, and of course, no blame for the incomplete of what I will present. Okay, so what are we going to talk about? I have divided the talk into 3 parts. The first part will just be some slides showing kind of what happens to fertility and marriage, maybe. I'll take some examples from the 1918 flu that I just put together, and we'll look a little bit at what's happening today. I've chosen an example from my childhood home county in Oregon. Then we'll have models. I mean, I have lots of question marks in this talk, so I guess models doesn't really need a question mark, but I guess I put it there to emphasize the kind of tentativeness of this. So the way I'm working through all this now, this is definitely a work in progress. And so I've divided the 3 types of models I've talked to into 3 kinds. The first I'm calling descriptive. The second will introduce some more behavior, demographic dynamics. And the third will introduce another type of behavior, contagious behavior. And these are some extensions of kind of what's there in the literature. They're not really, they're small steps forward, or kind of applying these existing models or simplified versions of them to the pandemic. So one title for this talk could be, what do existing models, or how can existing models be used to understand what the impact of the epidemic will be afterwards? And then I'll do some discussion. If I have time enough, I'll talk a little bit about formal demography, and I pulled a screenshot from Twitter. So if we have time for that, we'll do that. Okay. And I would like to stop also to answer questions in the middle, which I find to be valuable. So Wolfgang, if there is a question, feel free to interrupt me, and I'll try to answer it on the spot. I think that's probably a good use of time if I remember to pause. Okay, so the Lee here is Ron Lee. The Hernes here is Gudmund Hernes from Norway. Okay, Ron Lee is from Berkeley. Okay, so let's just begin with just some examples to see what kind of what happens after a pandemic. We have the 1918 flu to look at, for example. And here is what happened in Sweden. So these are just simple counts of births. It happens to be close to 10,000, but these are actual numbers. This is from the Human Mortality Database. A nice thing about the Human Mortality Database is that as its inputs, it uses monthly birth counts. So you can get long time series for counts of birth by month in many places. I'm sure interesting for studying seasonality and things like that. But here we're marching along. Sweden was not in World War I. So if we would look at Italy or France or Germany or something, they would be very low counts of births, because the men and the women are separated because of the war. The men are at the front. But in Sweden, there's no real effect of World War And so you see counts of births are declining very slightly. I'm not quite sure what's going on here, whether this is population composition or whether it's fertility rates per se. And then the pandemic hits. I'm not exactly sure when the pandemic hit in Sweden. I know the timing was a little bit different in Europe than in the United States, but you can see, boy, do births go down here at in the year after. This red part is the 12 months of the year after, and especially here. And then by the end of 1919, they've already bounced back up, and you get kind of this rebound or this, super compensation, where there's actually more births that are gained than are lost here, and fertility rates stay fairly high, although they decline, they begin their decline again. I shouldn't say fertility rates, birth numbers. Okay, so there's an immediate boom, and it seems to last quite a while. Okay, so let's look at marriage. The story is less clear. But this is the U.S. marriage rate. Now, this is from a book by Paul Jacobson, I believe, the old census guru, the U.S. Census, who studied marriage for many years. And this is births per 1,000 unmarried women. So this is a little bit more refined demographic measure. But we see the marriage rate is kind of rising a little bit, bouncing around. Then the year of the pandemic. This is not the year after as before, because the marriages were canceled immediately, not with births, we get a 1-year delay because of conception time. And then the year afterwards, it's not as if all of these marriages were just moved to the year afterwards. We still have less than we had the year before. And actually 2 years afterwards, we have a big boom. And then afterwards, things seem to stay high and then recede back to normal. So there's a delayed boom. What I mean by delay is it's not immediate. And there seems to be some persistence of the marriage boom. Okay, so what's happening today? Well, we haven't seen the results for births yet, although there's some very interesting papers. I think one of them is being presented at this conference using, say, Google searches and things like that, coming from a collaboration that I know some of the people are at Max Planck. But let's look at marriages, because we can already see what's happening with those. So I went to my home state of Oregon. They publish birth counts every month. This is my Lane County, Oregon. I grew up in Eugene. And we see in 2019, there's a seasonality to marriage, lots of summer marriages, very few winter marriages. And in 2020, we were started off very well, lots more marriages. Then the pandemic hits. Already in March, things are being canceled. In April, they're being canceled. In May, not such a big change. I was surprised by that. But then June, the bottom falls out. July, there are very few marriages. These are not weddings. These are marriage registrations. So it's not just the ceremony was canceled, but people decided not even to register their marriage, to get married. August, interestingly, very similar number. And then September, the bottom falls out again. So we see big declines in marriage, on the order of 40%. Okay, so and by all, and again, citing that work from Max Planck and from others, there's every expectation that birth rates are going to decline next year when the babies start not being born, the results of the conceptions that did not happen this year. And I think the estimates are something on the order of about 15%. Okay, so unfortunately, the pandemic is not over. And I know this whole conference is struggling with what is even happening during the pandemic, but especially since we're working with kind of modeling fictions, we might as well apply them to the future. And so let's look at already what's happening after the pandemic. And we have, kind of two simple questions, I think all of us, in terms of what's going to happen to at least for births and marriages. So the first thing is there going to be a boom? Will there suddenly be a big recovery? Will let's say the pandemic ends sometime gets under control sometime 2021? Will there be a big boom the following year? And the second question, which actually I was talking about this with Wolfgang about child education, will there be kind of long run effects on people's productivity and things like that? Well, in the context of fertility and marriages, I guess we can think of that in terms of cohorts. So we can ask, will cohorts recuperate? Will they get back all the lost events in some sense? So this is about a short-term effect, and this is about what will there be any effect over the long run for cohorts or for individuals. Okay, so this is what we'd like to know. Our models are not going to tell us this. What can we expect from models? Well, we have to scale back our questions to things that we hope the models can answer. We can ask something like, under what conditions might there be a boom or bounce, not will there be a boom or bounce. So the models can help us understand what these conditions are. Or what are the dynamics or assumptions that we would need for cohorts to recuperate. So we're not going to get predictions from these models. And in fact, everything I'll show you, I think, is simulation results. But that's what we're using the models for in order to understand what are the dynamics, the conditions, the assumptions that lead to different outcomes. Okay, so let's start simply with descriptive models. And again, I apologize for doing kind of hard to think about things at 5 o'clock at night, but I hope we'll start easy. And I've tried to at least use a simple font so it'll look like it's simple. Okay. So I don't know if demographers in general, I don't know if this term descriptive models is really, it's not a term of art, but I think this came from a discussion I had with Ron Lee the other day. We were talking about autocorrelation, and I was saying, well, here you can get autocorrelation just by setting up the model this way. And Ron was saying, yeah, but what does it mean behaviorally? That's just a fact about random variables. What does it mean in terms of actual human behavior? So he was pushing me. So I'm using the descriptive models in terms of that sense. They're somehow incomplete. They don't quite tell us enough, but they're still useful. Okay. Okay. So we'll do two types of descriptive modeling. The first models, one I'm calling rescheduling. And this is what, I think non-demographers imagine whenever you talk about, well, things will just be delayed. Okay, so here I have kind of a pseudo Lexis surface. You can think about some age here and time here. And in this world, everybody's having they're having 1x every period at the same age. And then the pandemic hits. They, in a simplified world, they have no x's in that period, and they just shift them to the next one. And then life continues as usual. Okay, so the period totals here, adding up all the events along the columns, are going to be 1x, 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 no x's, 2x's, 1x, 1x. So this is kind of you get this boom, you get all of the babies back, and you immediately go back to you have one very unusual year, and then you just go back to normal. Okay, and so this is, I think, things are just simply rescheduled. This is what would happen if all those weddings being canceled were just, cancel my booking for May 25th. Let's change it. Is May 25th open next year, 2021? Then you reschedule it for that year. And so we'd have, all of the canceled events would just happen immediately afterwards. Okay, so what did we assume here? Well, two things, I think. First, that all of the births or the weddings or whatever they are occurred just later than planned. So we didn't, just the number of X's didn't change, I just moved it. And the second assumption here is that immediately after the pandemic ends here, you go immediately back to normal. So you notice that this next X has the same height as these previous ones. So you could think of this as, age, and this could be weddings of 18-year-olds, and this could be a wedding of a 19-year-old, and the new cohort coming up on the diagonal just simply goes back to having its weddings at the same age, 18. And so we get the two weddings in 1 year. So you essentially return to the old normal, that is this pattern. Okay, so that's rescheduling, and rescheduling would involve an instant boom, and it would immediately disappear. That would dissipate immediately. Okay, let's look at. So this is what I think people imagine if you're talking with your uncle or something, and you're talking about demography, or your aunt, and you talk about timing changes. This is, I think, what they imagine. But demographers, of course, are cleverer than that, and they have usually another model in mind, especially for long-term changes, and that is postponement. So Bungartz and Feeney, or myself, or many other people who worked in this kind of postponement literature have this kind of setup in mind. So things are going along normally, and then the pandemic happens, and the events are shifted. But then after the pandemic, people decide to start at the post-pandemic time. Okay, so this is interesting. This is what happens when, say, age at birth goes up for the population in general because they have higher education or something like that. And so, all the cohorts born after the pandemic start having their children later, or getting married later, and the period totals look quite a bit different here. You've got the 111 before, then the 0 that were the same up to here, but the year after the pandemic, you just go back to having 1, and that stays 1 forever in the future. And we've actually, if you add up, if you did a cumulative total of the postponement model compared to the rescheduling model, you'll see there's an extra birth here. So you're always behind by 1. You've actually lost this birth. Now, there are interesting ideas about, well, the population now has more demographic potential, and if ever the next cohort did things earlier, you'd get back the birth, fine. But this is the story we generally see with postponement, and in this story, we would see no boom at all. We would just see kind of a recovery. Now, what do we assume? Well, all births still occur. They're just later than planned, so it's the same first assumption. But the second assumption is different. We stay at the new normal rather than return to the old normal. Okay, are there questions about this setup? Okay, it at least allows me to pause if I'm waiting for a question.
It's harder to ask for questions in this online setting, but I think you can just go ahead.
Okay, full steam ahead, full steam ahead. Okay, so now let's, so these models don't tell you why things happen. They just say, well, if you move things around like this, these could be X's, or they could be babies, or they could be weddings, or they could be anything. There's nothing demographic about this. We're just moving things around. So let's introduce a little more behavior, and for that we'll turn to Ron Lee and his pioneering paper on moving targets. And I actually didn't read his paper, but it's so much in the air here for preparing for this. I just kind of wrote down a model fresh from scratch. So it may be exactly the same as Ron's. I'm forgetting whether it's exactly the same as Ron's paper or not, but it's a simplified version of it. Okay, so Ron has this idea that there's a moving target of how many children people or cohorts want to have. And so cohorts have a target family size. And then fertility is just happening at a constant rate. So this is really a model about marital fertility, or fertility among those who are eligible, who are considering having children, who are kind of started their childbearing. And so if you want to have 5 kids and you have 2 kids, then you have 3 kids remaining to have, and you have some share of those 3 kids, some constant share, constant rate, each time unit. And then the birth timing, when you actually have the children, and the period dynamics, period level, is an output of the model, not the input. Before, timing was an input, if you remember. Okay, so how does this work? So here's some equations. The fertility rate is going to be this kind of fulfillment rate times the unachieved family size target. So fertility rate is our traditional f of x. X here, I should say, is years after the onset of childbearing. It's kind of a duration. It's not necessarily age. But let's say everybody considers starting childbearing at 20, so it could be age minus 20, but more realistically, it could be, say, marital duration or relationship duration or something like that. And then we have cumulative fertility here, that's big F of x, and the target. And so if the target is 5 and cumulative fertility is 2, then this number would be 3, and alpha would be some rate. So in this simple example here, I said, okay, target fertility is 2. People have already had, this cohort's already had by age x, by duration x, 1 child, so their unachieved fertility is 1. The rate, it turns out to be about 0.3 if you estimate this with contemporary populations in industrial societies. And so the fertility rate here at this age would be about 0.3, I think, 0.3 times 2 minus 1, or 0.3. So that's the way this works. I think I've walked through all this. Okay, this desired family size target here, I just have it as capital T, but in the real model, what Ron's interested in is he lets T vary by period. So that's an interesting twist. And then capital F of x, I'm sorry, the notation here is just capital F's are going to be cumulative of little f's, kind of like in statistics where you have the density and the cumulative distribution function. Okay, so the innovation here is rather than letting t vary, or in addition to letting t vary, we might or might not do, we can let alpha vary by period. So this 0.3 in normal times, it might be 0.3, but in a pandemic, maybe this number will be closer to 0, or maybe it'll be 20% lower or something like that. So the innovation here is we can let alpha, which Ron takes to be a constant, vary by period. Okay. So this is, I've been working with Tom Cassidy on solving. This is a differential equation, and depending on what you do for t and alpha, there are different solutions for it, and we're trying to get something that is tractable and interpretable and all that, but we're still working on that. So here's a simple example. The target, say, is one child, and people have half of their remaining unfulfilled fertility every unit of time. So when at the beginning, they have one unfulfilled child, so they have half of that, which is a half. After that, they have half an unfulfilled fertility target, so that half of that would be a quarter. And then after that, they've had 3/4 of a child. They're aiming for 1, so there's a quarter left. Half of the quarter is an eighth, et cetera. So this is a cohort moving along. You see that the profile is not given. It's a result of the model. It's actually the solution to that, to this kind of differential equation set up here. And we needed an additional initial condition to play it out. So imagine now that this is one cohort, and we have another cohort here, and another cohort here, and another cohort here, and we can fill those in. Here we go, and now we can look at the period totals, and we can add up the births at different durations. This is assuming that we're controlling for cohort size and that sort of thing. Maybe these are rates, or if all cohorts are the same size, they could actually be counts of births. If we add these up and we go to continued durations, then we'll get, in this particular example, we'll get 1, 1, 1, 1, 1, and that'll just happen forever, which is, I guess, makes sense since the target was 1, and since in a stationary type setup, stable setup, the cohorts and periods will be the same. So we know that they add up to 1 going this way, and so they since nothing's changing, they'll also add up to 1 in periods. Okay, so what are we going to do next? Well, obviously we're going to alpha change, and we're going to have a bad year. So let's see what happens when that happens. So here I've let alpha be 0 in this year. And so this, okay, let's see what happens the year after. So ignore these totals at the bottom for now. Well, the next cohort comes in, it still has the same target of a half. It has no, of 1, sorry, it has no, it has the stock of fertility is 0. Alpha is a half, so it has a half. This is just like it used to. Okay. The next one, well, its stock, if we kind of go this way, is going to be 0. So even though it's already duration 1, it's going to feel like it's duration 0. And so it's also going to have a half. Remember, before it would have a quarter. And then the duration 2, it's the same story. They'll behave like duration 1 because it's as if this year didn't happen in terms of the cumulative fertility. Okay, so it goes a half, quarter, eighth, 16th, et cetera, the total will be 1 up here, plus you'll get an extra half, and the total will be 3 halves. And then the next year, it's more complicated, but you get 5 quarters, and eventually this will just decline geometrically back to 1. And interestingly, we'll get all the babies back. The minus 1 here will equal plus a half, plus a quarter, plus an eighth, et cetera, et cetera. So we'll get all the babies back. And we didn't say, all we did in this model, we didn't say when the babies would happen. We just said there are no babies that happened in this year. And then the model kind of takes care of the rest.
You have about 5 more minutes, Josh.
5 more minutes in the whole talk?
Yeah.
Okay.
7, it's fine, but I think you have to speed up a little. Okay,
thank you. So this is what it looks like when you simulate this and you see what happens. Now, if we change the target, the model is very sensitive to the target. And if you change the target just a tiny bit, here's the new target was 1. If you change it to 0.99, it turns out there's no boom at all. Okay. And if you change the target even more, say by 10%, 5%, you actually get kind of a whimper. So here we got a boom, here we got a bounce, here you get a whimper. And if you change the target even more, you get kind of a thud. Fertility keeps falling. Okay, so the point, actually, this is the big point of the talk, is that lots of things are possible. And these are very small changes in the target. And we, the nature of what could happen is just very, very uncertain here, because we don't know what's going to happen to the target. Okay, so now I have a challenge, because I am I'm halfway through the talk, and I have 7 minutes left. So let's sum up where we are here. So this is a super simple model, but still creates complicated dynamics. Even small changes in the target have very large effects. Perhaps the boom after the Spanish flu in Sweden was consistent with no change in target. This looks a lot like the Swedish example. What's going to happen with COVID today? Well, the target is expected to decline. I think we all expect that because of economic difficulties getting started for young people, making a boom unlikely. But will we get a recovery whimper or thud? I don't know. Well, there's maybe a slightly different perspective. Maybe this is wrong. Maybe things like Trump's demise and the pandemic's end will bring about a new spring and targets will increase. That's something we could use the model to see what would happen if targets would increase. Okay, so now the next 20 minutes, I guess I was going to use to talk about diffusion models, but maybe I won't. This is just another way to set things up. And we can have targets not be set, that capital T, but rather we can have the amount of fertility or the amount of marriage be something endogenous that comes out of the model. And so social contagion and social diffusion models will do this. I think I should probably skip all of this because this would take time to explain. But this is a kind of diffusion model where you have the number of marriages depending on the number of marriages that have already happened and on some age function. And so things are spreading out. And when you have a decline in marriage, say due to a pandemic, then it's going to affect the stock of marriages, just like it affects the stock of births. And you get, here's what happens if there's no shocks. This is what this model ends up looking like. And if we have a shock, then what happens is that, so here I have the shock happen at say some arbitrary age 20, then you see because there are fewer people married, actually the pressure to get married is smaller. And so we are higher than we used to be, but we're much higher than we would be had there been no pandemic. So you don't really recover relative to the baseline quickly. And actually only much later do you have higher birth rates, or in this case, marriage rates. So you never actually catch up. Here's the cumulative stock. You fall behind and you get a little bit closer, but you never actually catch up. So there's no boom and only some recuperation. So what's interesting about this is that all of these dynamics of when this crossover is, when there's more fertility, when there's less fertility, is not an assumption. It's just something that comes out of the model from the setup that we had. So here's what happens if we do this with a bunch. I had the shock happen at 20, and we can have it happen at every age. The same shock happen at every age. And here's what happens. You don't get a boom right after the pandemic. Instead, you've still got a lot of cohorts being in this stage where they're marrying less, and then eventually lots of cohorts are out here. And so there's actually a boom much later, here in this case 10 years later, and it lasts, and then you go back to normal. So this, I think, looks a lot like what we started with here, where you get a boom. It happens a little bit late, and then it goes a lot longer. Okay, so let's do two specific conclusions. The Lee model suggests that the period birth rebound will depend very strongly on what happens to the target. The Herney's model, which I didn't spend much time on, suggests period partnership could rebound, and even if cohorts don't recuperate. So that's interesting. So even though we get back, to normal for the cohorts born way out here, the cohorts never recuperate fully. And I can say you can set up a similar type of a model for fertility. This is just marriage here. Okay, so just to finish up here, the things that the models tell us is that things are very unpredictable. Anything goes right after the pandemic ends. We can get a boom, a bounce, a whimper, or even a thud. Patience, even a short-lived shock could reverberate for years. We'll have to watch this thing play out. And that's this picture here. It takes a long time. Here we have 10, 15 years later. And these kind of lagged effects will be even stronger in the real world. In all my simulations and setup, the pandemic came and ended at the same time for everybody, and it was very crisp in terms of starting and stopping. The epidemic won't end suddenly for everyone at the same time, and we already saw that with, say, the Great Recession. I think I'll skip future theoretical directions. And I'll end with just a little bit of what I alluded to earlier about what formal demography is and what it can be used for. So here is a former student of mine, a product of Berkeley, who's now a professor at University of Toronto, Monica Alexander. She's thinking and writing about formal demography and realizes she doesn't have a good definition for what it is. And Leontine, also one of our guest faculty, who loves Bayesian demography, writes, formal demography, elegant mathematics to solve a demographic problem under assumptions that never hold true in practice or using data without measurement error. Statistical demography, formal demography extended to real populations and using data with measurement errors. Well, I don't think this way. I think that formal demography is not solving a demographic problem. It's providing us a way of thinking that can be useful. And I think that the empirical work, a lot of what we have at this conference, and formal work are complementary. For one thing, models can help us work through our thinking, and for another, they can point us to what it is we want to measure in the first place. So as a conclusion, I'll just say that working on this has made me more interested than ever in terms of measurement. And the thing I would want to measure would be, fertility intentions, and not once every few years, but very, very frequently. Maybe what we need is some kind of, high frequency birth intentions barometer, where we're asking people about how they feel about their fertility targets and how many kids they want to have all the time. And we can kind of follow this and know which world we're in quite early. And maybe we want to also be doing this in terms of cohabitations and marriage. So the new field of digital demography and using the internet and this sort of thing to gather information about people maybe is a new, it would be nicely applied to something like birth intentions. And the idea would be just some kind of very high frequency, I don't know, every week, every month, every quarter, something like that, where we're actually tracking populations and seeing how people feel. So thank you for bearing with the slowness of the first half of my talk and the fastness of the second half. I'm delighted to answer questions.